Hi. So, in the last video, we looked at explaining the reasoning behind how we go about solving first order non homogeneous recurrence relations. I'm going to recap some of that vocab in a few seconds. This video is going to focus on really just the method behind it, getting into the steps you need to go through, and looking at some more unusual or more difficult situations. So, firstly, just to recap all the words are through there. So when we're talking about first order recurrence relation, that's saying that we're only looking at recurrence relations where each term only depends on the previous term. So in this case, in the example, you can see un plus 1 depends on un. We don't have another un minus 1 or un plus 2 involved. If a term depends on the previous two terms, we'd say it was a second order recurrence relation. Now, the non homogeneous bit, if we had un plus 1 equals 2un, and that was all, then we'd say that it was a homogeneous relation because all that's happening is we're doing something to our previous term. In this case, we've then got another thing added here. In this case, it's a plus 4n. Anything that's an extra term that isn't directly related to the previous term is what makes it non-homogeneous there. When we're asked to solve, we're given an initial condition here, so we're looking for a particular solution of recurrence relation that solves the relation we're given and fits that initial condition. So there's a few steps we're going to go through. If you haven't watched the previous video, make sure you watch that first. My first step that I'd recommend, even though you could get away with this one, is rearrange it to get all your UNs or your UN plus 1s and everything onto one side. So if we do that, we're going to get UN plus 1, subtract 2UN, but the 4n doesn't have a U involved, so I'm going to keep that on that side. Rearranging that just is going to allow us to deal with each part separately a bit more easily. So first step, rearrange. Our second step is we want to look for the complementary function. Now, as a reminder of that vocab, that is the function which will solve this recurrence relation if it was just equal 0, if it was a homogeneous relation. So we want to find the complementary function, but I'm generally going to be lazy and just write the CF. So in order to do that, we're wanting to solve un plus 1, subtract 2un is equal to 0. You don't have to rearrange at this point, but just as a reminder, if you can't say what it's going to be straight away, this is the same as saying un plus 1 equals 2un, and this is just a geometric sequence where we're multiplying by 2 every time. So from the previous video, we should be able to recall, or from what you know about from single maths, you should be able to recall the general solution to that is just going to be, I'm not going to bother writing un there. A complementary function is just going to be some number, I'm going to use p, times by 2 to the n because our common ratio is 2 there. So that's our complementary function. Now, so far though, we've only solved equals 0. We need to get something that's going to give us this 4n and then combine these two ideas together. So we need to look at what we're dealing with on this right-hand side. We've got 4n. That's a linear function. If we had a n squared, we'd have something more complicated. Being a 4n is a linear function. We've got to think what's the most possible linear function we could have and use that as our trial function. So this part is trying to find any function that would work, no worrying about the initial condition. And by doing that, we want to say, well, we've got to choose a linear function. So we're going to try a trial function of an plus b because that's the most linear, that's the most general linear function we can give. You might be thinking, well, there's only a 4n there. Why are we trying a constant? If you're thinking that, pause the video, give it a go, and you'll see where it breaks down. This gives us the generality we need in order to be able to solve this. So we're going for the most general linear function possible because it was the linear function on the right-hand side, as in the highest power of n was 1. And now we're going to sub in this into our rearranged recurrence relation from step 1. So un plus 1 is going to be a brackets n plus 1 plus b, and then we're subtracting 2 lots of un. So subtracting 2 lots of a n plus b, and we know from step 1 we want this to be equal to 4n. Now doing some expanding and simplifying, if we expand the left-hand side, we're going to get an subtract 2an, which will give us negative an. We'll then get plus a, and plus b minus 2b will give us subtract b is equal to 4n. At this point, we can compare coefficients because we want this to be true for every value of n. So we can treat this like we would with an identity. The coefficients of n on the left-hand side is negative a, and on the right-hand side is 4. So negative a has to equal 4, or a has to equal negative 4. And then on our constants, we're going to get our a subtract b on the left-hand side has to equal 0. So if a is negative 4, b is also going to have to be negative 4. And our successful trial function is now just going to be, going back to we had a plus b, so it's minus 4n subtract 4. So we've got our trial function now. Once we've got our complementary function, which we did in step 2, and our trial function, which we've done in step 3, our general solution is just the combination of those, just adding those together. So step 4 is always, once you've got those, just saying that our general solution, so we're still not worried about the initial condition yet, but the general solution, un, is always the complementary function plus the trial function. And we're going to get from our step 2, p times 2 to the n, and our step 3, subtract 4 and subtract 4. Now, if you weren't given an initial condition, this is as far as you could go. But we were told u 0 equals 6. So we're on to step 5, our final step, finding our particular solution, a value of p that will allow us to fit that initial condition. So using the initial condition, subbing in n is 0 into both sides, we're getting a u0, which is 6, is equal to p times 2 to the 0. Well, that's just p. Subtract 4 times 0, which is 0. Subtract 4, and we're going to get p is equal to 10. So our particular solution, remember our particular solution is the one that solves both the recurrence relation and the initial condition, is un is equal to 10 times 2 to the n, subtract 4n, subtract 4. Sorry about that, my pen's just playing up a little bit there. Okay, so just to recap those steps before we look at some other situations we might come across with. Rearrange, that's optional, but it'll make your life a little bit easier. Find the complementary function by making the right-hand side equal to 0. This is turning this into a geometric sequence, which is nice and easy to deal with and gives us the general part. We're then looking for any function which solves this relation without worrying about the initial condition. And here we're going back to having it equal to 4n and solving this. And we're choosing our trial function to match the form of that right-hand side. So in this case, it's a linear function. We're going through, we're doing some algebra, getting those, and then we're adding together our complementary function and our trial function. So what other trial functions might we have to come up with? I'm going to keep with very similar examples here, but look at what might change. So if instead on the question, I'd given you un plus 1 subtract 2un, so the same left-hand side, but equal to 3n squared plus 5, say. Well, in this case, I've given you something that's quadratic on the right-hand side, so your trial function would be the most general quadratic you could do. You'd go for an squared plus bn plus c. You get more algebra to go through, but it works through in exactly the same way, and you can compare your coefficients in exactly the same way. If the right-hand side is a polynomial of order k, then you're going to pick a trial function, which is the most general polynomial of order k, but I doubt that working with polynomials you'll ever get anything bigger than the quadratic in these cases. For first order cases, your complementary function is never going to get more complicated than this, but your trial function might, depending on what's on the right-hand side. So I want to look at some different cases about how that might appear and how your trial function might change. So it won't always be a polynomial. So let's consider a new example, but very similar to the previous one. So I'm going to start already with the rearranged form, un plus 1 subtract 2un. So exactly the same left-hand side as last time, but I'm going to say we want it to equal 9 times 5 to the n on the right-hand side. So as you can see, definitely not a polynomial now. Now, when we're picking a function, what we're saying is we want to pick a un where we sub this in and we happen to end up with 9 times 5 to the n. You're probably not going to be able to spot that straight away. It would be very impressive if you could. I certainly couldn't. But what we can expect is if we want to end up with a 5 to the n, we're going to have to start with a 5 to the n in there somewhere, otherwise it's not going to appear from nowhere. So our first couple of steps would be the same, but when we get to step 3, our child function in this case is going to be un is equal to some number, again, which we're not going to know, times, so I'm going to use an a there, multiplied by 5 to the n. We're going to hope this works. We'll go through, we'll see that it does. So we're going to sub this in to both sides and pick the a so they work. So un plus 1 would be a times 5 to the n plus 1. And then we've got subtract 2un, which is 2a times 5 to the n. And we want this to equal 9 times 5 to the n. Well, we've got to do a little bit of power work with that first term, but it's not too bad. We just need to recognize that a times 5 to the n plus 1 is 5a times 5 to the n by taking out one of our 5s from the power. And then we're in a position to just factorize, and you might even get away with factorizing, to be honest. If we factorize that 5 to the n out, we've got 5a subtract 2a, so it's just 3a lots of 5 to the n is equal to 9 times 5 to the n, and we can now spot that we're just going to need 3a equals 9, or a is equal to 3. So our child function, in this case, is going to be 3 times 5 to the n. And that's going to work fine, and then you're going to go through the rest exactly the same as before, so I'm not going to worry about going through that. We're just going to get 3 times 5 to the n as our child function. Add that to our complementary function, we've got our general solution. And if we wanted to get any initial conditions, we could do that the same as before. So we seem to be good. That's about as complicated as you're going to get on the right-hand side in your first order relations. Most of the time we'll come back in second order and look at some other harder cases. But there is one weird, tricky special case you need to be aware of. And it looks like it's going to behave the same as this, and then it doesn't. So that's why we need to be very cautious and watch out for it. And that is, the complication we're looking at is starting the same on the left-hand side. We're still going to go with un plus 1, subtract 2un. And on the right-hand side, I'm going to say times 7 to 2n. And it looks like, well, it's just going to be a times 2 to the n. I want to go through this. I want you to see where it falls down, and then you'll see why we have to make a somewhat unusual step. So this next bit is going to be an incorrect approach, but it's an important approach to see, because you're definitely going to fall into the trap at some point, and it's worth having seen in advance. So if we go for the child function of un equals a times 2 to the n, what's going to happen here? Well, we're going to get un plus 1, which is a times 2 to the n plus 1, subtract 2un, which is 2a times 2 to the n, and we want that to equal 7 times 2 to the n. We get stuck because, hang on, we've got a times 2 to the n plus 1, and our second term is a times 2 to the n plus 1 if we move that 2 into the power. So this equals 0, and it's impossible that we can get it to equal in 7 times 2 to the n. Why should we have seen this coming, and how can we watch out for this to avoid wasting our time like this? If we go all the way back to our complementary function, I'll have to scroll up a little bit here. Our complementary function, any term of the form p times 2 to the n solved this thing equals 0. And this was of the form something times 2 to the n. So it was always going to give us 0. There was never going to be any value of a that could give us anything different there. So if our child function, or our natural choice of child function, appears in our complementary function, it's not going to work, and we're going to have to do something different. So what do we change? Well, whenever we get a child function appearing in our complementary function, we're going to multiply our child function by n. So to show what we're going to do here, we're going to say instead, we're going to say we want a trial function of un equals an times 2 to the n. It looks a bit unusual, but trust me, it works in practice. We're about to see it happen. So we're now going to sub our trial function in to our recurrence relation. We need to be careful that all our n's get replaced with n plus 1s. So when we do that, we're going to get un plus 1 is going to be a bracket n plus 1 times 2 to the n plus 1, and then we're subtracting 2 lots of un. It's going to give us this, and we want it to equal 7 times 2 to the n. So because we've got a 2 to the n on the right, I'm going to try and make them all 2 to the n's on the left. So expanding, we're going to get 2an times 2 to the n, and we're going to get plus 2a times 2 to the n, if we're making it in terms of 2 to the n there. And then, just zooming in just so you can see this more clearly with my writing, and then we're subtracting 2an times 2 to the n. Just keeping the right hand side there to make it clear. Now, this term and this term are going to disappear. They're just going to simplify, and all we're going to be left with on the left-hand side is 2a times 2 to the n is equal to 7 times 2 to the n. So now, comparing, we're going to get our 2a is equal to 7, and a is 7 over 2, and our trial function is going to be equal to 7 over 2 n times 2 to the n. So most of the time, we're picking a trial function that just is the general form of whatever we've got on our right-hand side. But if we come to a situation where our trial function is contained in our complementary function, we're going to have to multiply that by n in order to work through and solve. Once you're there, you're doing the same as before, add it to your complementary function, and if you've got initial conditions to solve, you can get those from there. Next videos are going to start looking at second order recurrence relations. So that's ones where a term will depend on the previous two terms and we'll have extra functions involved as well. Thank you.